Well, hello, ladies and gentlemen. We are going to be moving on from superheated vapor, the saturation dome, going to be moving on to what's called ideal gas behavior. We're going to be looking at a simple expression relating pressure, volume, and temperature for a gas. In other words, the ideal gas behavior that I've been talking about here. We're also going to look at a quantity called the compressibility factor Z. Compressibility factor Z, we're going to look at what's called the compressibility chart. And then we're going to deal with cases where the compressibility factor is approximately equal to 1. And in that case, there's a very simple relationship relating pressure, temperature, and volume for a gas. And then we'll do an example today. So why don't we get started here by kind of reviewing what we did for the last couple of days very quickly. So we have temperature, specific volume, we have the saturation dome. Here is an isobar. So here we have super cooled liquid, SCL. And then here we have saturated mix inside the dome, saturated liquid, saturated vapor on either side of the dome. And then out in here, we have superheated vapor, okay? Now, what we finished off last time was to get properties of a superheated vapor, we use what are called superheated vapor tables. Sometimes they're called steam tables if we're dealing with H2O. So we use superheated vapor tables. And I think I showed you this last time. So let's have a quick look at a superheated vapor table out of the text. So this is a saturation table for H2O. B4. Superheated vapor table for H2O. Pressure, temperature, specific volume, internal energy, enthalpy, entropy. So you can, if you give me a pressure and you give me a temperature, I can presumably go to a superheated vapor table out of the notes or the textbook and extract out the various properties, okay? So that's one way. So let's say we're interested in getting a specific volume for a given pressure and temperature. Well, we would obviously use a table. May have to do a little interpolation between temperature or pressure points in order to estimate a specific volume, for example, okay? So we would get properties from tables, superheated vapor tables, out in the superheated vapor region. So that's how we would get properties. Now, let me show you another way of getting some properties in the superheated vapor region. So if we have a superheated vapor, we can also use what's called the compressibility factor. Z is the compressibility factor, and it's equal to the following quantity. Pressure times volume divided by mass times the gas constant T multiplied by temperature. So if we have a container, let's say, and it's a gas, it has a pressure, it has a temperature, there's a certain amount of mass in it, and it has a volume. Pressure, volume, temperature, and mass are all related by this equation here. Z is some quantity that's looked up using some kind of a table or a chart. And Z, the compressibility factor, is equal to pressure times volume divided by mass times the gas constant times temperature. Now, hopefully you've heard from physics of the ideal gas law. We're getting to that right here. If you remember, If you set Z equal to 1 and you have all this quantity equal to 1, then you have what's called the ideal gas law. We're going to get to that in just a moment. Okay, so if we have a superheated vapor, we can use the compressibility factor to relate pressure, volume, temperature, and mass for a gaseous material. First of all, before we start using any of this, I do want to point out what this R is, okay? And actually, before we do that, I want to show you there are two versions of this equation. There's pressure times volume. In this one, I have a mass times a gas constant times a temperature. We also have the number of moles, N, times a universal gas constant, T, times temperature. So we have two different versions here. One involving the mass and one involving moles, okay? Number of moles or molecules. So we could have N moles inside of our container of gas as well, okay? So in both of these equations, we have this R term here. One's a little bit different. The first one, so what is R? R is equal to the gas constant. Gas constant. It is material specific, and it has units of energy per kilogram, or energy per unit mass, per degree temperature. In metric, it would be, let's say, a kilojoule, or a joule, let's say, per kilogram degree in Kelvin, okay? That's what it would be in metric. Okay, so R is the gas constant and is materially dependent. RU is the universal gas constant. Universal gas constant, i.e. U for universal. Universal gas constant. That is a constant which is not materially dependent and is valid for all gases. So this guy has units of energy per mole per degree. If this were in metric, it would be joule. Well, it could be kilojoule per kilomole. Kilojoule per kilomole degree in Kelvin. If it's a metric, then that's the unit the universal gas constant would take. All right? The value of the universal gas constant, by the way, running out of space here. The value of the universal gas constant, RU, is equal to 8.314 kilojoules per kilomole degree in Kelvin, okay? So 8.314 kilojoule per kilomole degree in Kelvin. That's the actual physical value of the universal gas constant. Now, let's say we have a material and we want to go from the universal gas constant and calculate the gas constant for a certain material. We want to start off with the universal gas constant, which has moles in the denominator, and we want to go to the gas constant, which is materially dependent and has mass in the denominator. Well, how do we go from moles to mass? We have to use a molecular weight. So note, the gas constant R for a particular material is equal to the universal gas constant divided by the molecular weight of the material. Let's make sure this works here. Let's look at the units here. I have energy per mole degree in Kelvin. I'm sorry, per degree. And then in the denominator, I have mass per mole. The moles cancel out, and I get energy per unit mass per degree. Okay? So, to get the gas constant, take the universal gas constant, 8.314, and divide it by the molecular weight of the material. And we'll do an example involving this as soon as we get through the material today, okay? Okay, so let's go back to this compressibility factor here. Let's go back to this compressibility factor. Now that we know what the gas constant and the universal gas constant are, you've encountered this stuff before, but let's make sure we're all on the same page. So again, let's write the expression for the gas constant, Z. So for a superheated vapor, pressure, volume, and temperature can be related according to the definition of the gas constant. Compressibility factor. Z is equal to PV over mRT. And I can also write this as pressure times volume is equal to N RUT. Okay? Just talked about the universal versus the gas constant. Okay, we can go between one and the other. You give me the material, I can calculate R from RU with the molecular weight. Okay? Now, let's look at how the compressibility factor is determined. Let's say we have a pressure and a temperature and we got a material and a certain amount of mass, and I want to know what the volume is or something. I want to use this equation. How do I get Z? How do I get Z so I can relate pressure, volume, temperature, and mass? Well, you've got what's called the compressibility chart. Compressibility chart. Compressibility chart. What the compressibility chart is the following. It is Z on the y-axis, the compressibility factor, a quantity called the reduced pressure, P-R-E-D-U-E-C-D, reduced, P reduced or P-R-E-D, P reduced pressure, and then curves of constant reduced temperature. T reduced. Okay? So I'll tell you what reduced means in just a moment. But what we have here is basically Z, the compressibility factor, as a function of temperature and pressure. That's basically what this chart will give us. You give me a temperature and a pressure, and I can look up the compressibility factor Z. Now, if you go to the text here, let's have a look here. Let's have a look at the text. Let's go to the textbook here. I'm sorry, the notes. Here we are. If you go look at page 28 out of the notes, here's the compressibility factor right here. You see on the y-axis we have Z, which is a function of pressure. This is specific volume right here, so that's volume divided by mass. That's why there's no mass in that equation. So it's a compressibility factor, which ranges from 0.2 up to about 1.2. Then we have reduced pressure on the x-axis. And then we have, as you can see, curves of constant reduced temperature. I'm using P sub R here in this plot and T sub R to indicate reduced temperature and pressure. Okay? Now, one thing to notice here, if Z is approximately equal to 1, the compressibility factor, If Z is approximately equal to 1, then this expression here, this relationship between temperature, pressure, mass of a gas becomes very simple. We get pressure times volume is equal to mass times the gas constant times temperature. If Z is equal to 1, or approximately equal to 1, you can put approximately here if you want, then I get PV is equal to MRT, okay? I also have PV is equal to NRUT, okay? If Z is approximately equal to 1. These two equations right here, these two equations are referred to as the ideal gas law. Oops, damn it, did it again. So here, if Z is approximately equal to 1, and that means this is 1 right here, then PV over MRT is equal to 1, and PV over NRUT is equal to 1. And then we get PV is equal to MRT, and PV is equal to NRUT. These two equations right here, under the simplified case where Z is approximately equal to 1, these guys are called the ideal gas law. Ideal gas law. Put a box around them. Okay, these are the ideal gas law. Hopefully you've dealt with these before in basic physics. Well, you're going to be dealing with it now. Okay? Ideal gas law. That's when Z is approximately equal to 1. So when Z is approximately equal to 1, when we have a good temperature and pressure range at which Z is 1, or nearly so, then the relationship between pressure, volume, temperature, and mass becomes very simple. And we can calculate properties for superheated vapor with relative ease if Z is approximately equal to 1. Okay? Now let's figure out where Z is approximately equal to 1, under what conditions. First of all, let's define what we mean by reduced pressure and temperature. What are these things? Well, T reduced, I'm just going to write TRED, and I'm going to get rid of this. Reduced, you can leave it. I'm just going to put a reduced there. T reduced is defined to be equal to the temperature of the gas divided by the critical temperature. The critical temperature, okay? And P reduced is equal to the pressure of the gas divided by the critical pressure. Now, these should be kind of familiar with you. Let's remind ourselves what these critical temperatures and pressures are. Let's go back to the saturation dome. Let's go back to the saturation dome. Let's go back to the saturation dome. So here's our saturation dome. Temperature, specific volume. Here's the dome. The peak temperature in the dome, the peak temperature on the top of the dome is equal to the critical temperature. This is the critical point. Critical point. So the critical temperature is the peak temperature in the dome. And there's also an isobar that goes through right through the very top of the dome. So this is the P critical isobar. Okay? And if you recall, where do we get these critical temperatures and pressures? Let's have a look. So we got our superheated vapor table, saturation pressure, saturation temperature. Very first table, B1. Chemicals, chemical formula, molecular weight. This is going to be useful here soon when we do some stuff with the ideal gas law. Critical temperature in Kelvin and critical pressure in bar for various materials. Okay? So critical temperatures and pressures are out of table B1. So T-crit and P-crit out of tables B1, okay? In the notes. Okay, let's figure out where the ideal gas law can be used. Where is the compressibility factor approximately equal to 1? That's the next question we have. When can we use this ideal gas law, Z is approximately equal to 1? Makes our life so much easier if we can assume this relationship between pressure, temperature, volume, and mass, okay? Well, let's have a look at the compressibility chart here. So the point is, Z is 1 right here, okay? So along this horizontal line, Z is approximately equal to 1, okay? Now, let's look at reduced pressure first. So here we have a reduced pressure of 0.5. Here we have a reduced pressure of about 0.25 right in the middle. 0.2 is a little bit closer here. And we can see that all these curves of constant reduced temperature indicate a reduced pressure, a compressibility factor Z starts to collapse towards 1 as reduced pressure goes to 0. So as reduced pressure goes to 0 and we go from left to right on the x-axis, the reduced pressure axis, the Z factor curves, the compressibility factor curves all collapse to 1. So the first thing we can think of is as reduced pressure goes to 0 or gets very low, Z goes to 1. So that's the first thing to say. So the first thing to notice is, as the compressibility factor Z as the reduced pressure goes to 0, P reduce goes to 0, Z becomes approximately equal to 1, okay? So as we move this way on the chart, for any reduced temperature, Z approaches 1, okay? Now let's go back to the compressibility chart. So low reduced pressure means that we can use the ideal gas law. Z is approximately equal to 1. What about temperature? Well, certainly for fairly low temperatures or fairly low reduced temperatures, so here's reduced temperature equal to 1, Z starts to vary very quickly as reduced pressure increases. So Z actually goes down to 0.2 for a reduced temperature of 1 at just 1 PR equal to 1, okay? So for low reduced temperature, Z varies very quickly with reduced pressure. So we don't want a reduced temperature that's too low. We want a reduced temperature that places us somewhere in here in the compressibility chart, okay? Now we can go up and reduce temperatures, 1.4, 1.5. Here's 2 right here, 2. So if we have a reduced temperature of, let's say, no less than 2, then we're on this curve or above this curve, and we have sufficiently low reduced pressure, let's say less than 0.2, then we end up in a small envelope right in here on the compressibility chart, very small envelope, and Z is approximately equal to 1. So I'm going to make the claim here. I'm going to make the claim for T reduced greater than 2 and P reduced less than 0.2, the compressibility factor Z is approximately equal to 1. That puts us basically, let me put in a few more reduced temperature curves. So this is T reduced equals 2 right here. So using this rule here, we end up staying right in this region where Z is approximately equal to 1. Okay, Z is 1 right there. Okay, so let's put a little box around that. I'm going to write it again. In fact, I'm going to write it right over here on the other board so we can clear up the clutter. So let me write the definition of the compressibility factor, and then write the ideal gas law, and then indicate the conditions under which we can use the ideal gas law. So Z is equal to PV over M RT, which is also equal to PV over N RUT. And for reduced pressure less than 0.2 and reduced temperature greater than 2, Z is approximately equal to 1. And these equations here imply PV is equal to M RT or N RUT. Okay? So why don't you write this in your notes somewhere? This is a very important set of information, and these equations pretty much encapsulate what we've gone over the last 20 minutes or so. Okay? Definition of the compressibility factor Z. Z is a function of temperature and pressure. Under certain ranges of temperature and pressure or reduced temperature and pressure, we can say Z is approximately equal to 1, and then we get the ideal gas law, okay? This is the ideal gas law. PV is equal to MRT, or PV is equal to NRUT, ideal gas law, all right? Okay, let's do a nice example involving a superheated vapor, and we're going to use the compressibility factor, and we're going to use the ideal gas law. And we're going to compare the values that we get using tables versus the compressibility chart versus the ideal gas law. So we can see how to hit a particular problem from all sides using these relationships. Okay? Let me pause this for a second. Okay, let's say we have a container of steam, or H2O. So given H2O, and this is going to be a vapor. In other words, a superheated vapor, all right? I have a pressure and a temperature here. We have a pressure is equal to 120 bar, and we have a temperature equal to 520 degrees C, 520 degrees C, okay? Let me show you a schematic here. So we have a container. So here's our H2O. And this container has a certain temperature, a certain pressure, a certain volume, and a certain mass, okay? So I want to find some things. Find. First of all, I want to find the specific volume. Find the specific volume. So this will be the first part, part A. Let's find the actual specific volumes using superheated vapor tables. So specific volume using superheated vapor tables. This is going to be my actual specific volume. The tables are correct. The tables give you the specific volume. And then I'm going to use the compressibility factor and find specific volume using compressibility factor Z. And then I am going to attempt to calculate specific volume using the ideal gas law. So V, ideal gas law, okay? I will attempt to calculate specific volume using the ideal gas law, all right? We'll see what our success is there. We'll see what our success. Okay, let's get started. So analysis. Part A. So specific volume is equal to specific volume of a superheated vapor. I'm telling you it's a vapor. You'll see in a minute that it is. Evaluated at a temperature equal to 520 degrees C and a pressure of 120 bar. 120 bar, okay? Let's go to superheated vapor tables. Let's go to superheated vapor tables in the notes. So B1, saturation temperature table, saturation pressure table, superheated vapor table. Pressures are located in the header. Let's see if we can find a 120 bar here. This is all table B4. They're just a bunch of tables being continued. 120 bar. Here's 120 bar. Temperature is given here. Pressure is here. Let's see, 520 degrees C. 520 degrees C, 120 bar. The specific volume with units of cubic meter per kilogram is 0.02781 equals 0.02781 cubic meters per kilogram. 0.02781 cubic meters per kilogram, okay? 0.2871. And this is from superheated vapor table, superheated vapor table B4, okay? So specific volume for part A is 0.2781 cubic meters per kilogram. Let's put a box around that. That is the actual or the true specific volume. The table, the superheated vapor tables are accurate. Let's move on to the compressibility factor. Let's see if we can estimate specific volume using a compressibility factor, Z. Oops. Okay, so we have our, so let's start working on B over here. Start working on B over here. We got our equations, definitions for compressibility factor. Now I want a specific volume out of one of these expressions. Specific volume is not volume divided by the number of moles, it's volume divided by mass. So I'm going to write that first equation. I'm going to write Z is equal to PV over M RT, and then I'm going to group the volume and the mass together, and I get volume over mass, and then I have P RT. Now this, of course, is specific volume, and so I get specific volume PRT. Let's solve this for specific volume. Specific volume is equal to the compressibility factor times the gas constant T times temperature divided by the pressure. All right? Now I have temperature. I have temperature, I have pressure, I don't have the gas constant R, I'm going to have to calculate it, and I don't have the compressibility factor Z. I have to look that up or calculate it as well. Okay? First of all, let's get the gas constant. Let's get the gas constant. Let's get the gas constant. So, oh, how do I want to do this? Got this in your notes? Hope so. I'll start working on the gas constant. Let's see here. R. R is equal to the universal gas constant divided by the molecular weight for the material. Okay? Now we have H2O. So molecular weight for H2O, what is that? Let's go to our text, our notes, and let's look up the molecular weight of H2O, water. Let's go to table B1. Water, molecular weight, 18.02 kilograms per kilomole. 18.02 kilograms per kilomole. 18.02 kilograms per kilomole. And that's from B1, okay? So that means our gas constant, R, is equal to 8.314 kilojoules per kilomole, degree in Kelvin, and then I'm going to divide that by the molecular weight. This is RU right here. Divided by the molecular weight, 18.02 kilogram per kilomole. The kilomoles cancel out, and I get kilojoule per kilomole, degree in Kelvin. And I get a gas constant, and this is going to be for H2O. So R, H2O. So we're going to have clear 8.314 divided by 18.02. 0.046. 0.461, and that's going to have units of kilojoule per kilogram, degree in Kelvin. Kilojoule per kilogram, degree in Kelvin. Okay? Kilojoule per kilogram, degree in Kelvin. So that's R for H2O. So now I got R for H2O. Okay? Let's get the compressibility factor. That's the last thing I need. So what is Z? Z equals what? What is Z? Well, first of all, let's go back and look at our compressibility chart. What do we need to know to calculate the compressibility factor Z? So Z is a function of reduced pressure and reduced temperature. Remember, reduced temperature and pressure are temperature and pressure divided by the critical temperatures and pressures. So let's calculate the let's calculate the reduced temperatures and pressures. So Z is equal to, so let's calculate the reduced temperature and pressure. So T reduced is equal to T divided by T critical for H2O. Let's see, the temperature is 520 degrees C. Critical temperature and pressure are going to be in Kelvin, so I need to add 273 to get it in Kelvin, degrees Kelvin. So let's look up the critical temperature for H2O. Let's look up the critical temperature for H2O. Table B1, critical temperature, water, 647.3 degrees Kelvin. 647 Kelvin. 647 degrees Kelvin. Kelvins cancel out, and I get a reduced temperature. Let's see here, 520 plus 273, divide by 647. I get 1.225. Okay, that's the reduced temperature, 1.225. What about reduced pressure? What about reduced pressure? P reduced. Well, that's equal to the pressure divided by the critical pressure. Let's see here, we got 120 bar. That's the pressure. What's the critical pressure? Let's have a look in table B1. Critical pressure for H2O, 220.9 bar. 220.9 bar. So I'm just going to put 220 down there. 220, 20 bar. Bars cancel out. Reduced pressure is dimensionless. And I get 120 divided by 220. 20 divided by 220. 0.54. Actually, 0.55. By the way, if you're thinking ahead on using the ideal gas law, where Z is approximately equal to 1, we're already in trouble here. Remember the criterion for using the ideal gas law is reduced pressure must be less than 0.2. We're at 0.55, almost 0.6. So clearly for part C, when we calculate specific volume based on the ideal gas law, we're probably not going to get a good result. Okay? In any event, reduced temperature and pressure, 1.2 and 0.5. So Z evaluated at a T reduced equals about 1.2 and a P reduced about 0.5. Let's get the compressibility factor from our compressibility chart. This is going to be kind of an eyeball affair here. It's going to be kind of an eyeball affair. Let's see here. There's our compressibility chart. So 0.5 is our reduced pressure, so we're along a vertical line going through here. And reduced temperature, what was that again? That was 1.2. Here's 1.2 right here. Here's my 1.2 reduced temperature line, that solid line. So I'm at 0.5 reduced pressure. And I go up to the 1.2 reduced temperature line. Looks to me like I get about 0.9 for Z. Somewhere right about here. You could use a pencil and a ruler and probably get a better result. But it looks to me like Z is going to be about 0.9. Okay? Maybe a little higher, maybe 0.91. I guess it's probably 0.91. I'm going to put that in. I'm going to choose 0.91. So Z is approximately 0.91. 0.91. Okay? And that's from the compressibility chart. Compressibility chart. All right? Okay, let's finish the calculation here. Let's calculate the specific volume for our H2O. We now have the compressibility factor is 0.91. So 0.91, gas constant 0.461, and that has units of kilojoule per kilogram degree in Kelvin. The temperature, Kelvin. Kelvin is the temperature unit in the gas constant, so we have to give temperature in Kelvin, so that's 520 plus 273. So what? That's going to be 793 degrees. 793 degrees Kelvin. And then the pressure is 120 bar. Okay? So let's crank some of this out here, and then we'll deal with the units in a second. Looks like we have some unit issues So 0.91 times 0.461 times 793 divided by 120. And I get 2.77 something. Let's look at the units here. Well, the kelvins cancel out, that's good, and I get a kilojoule per kilogram bar. Whatever that is, that doesn't look like a density to me, a specific volume. Specific volume should be cubic meters per kilogram. Well, let's try to, first let's get out of the bar and let's get into kilopascals. Let's get out of the bar and get into kilopascals. Let's see, there are 100 kilopascals per bar. So 1 bar equals 100 kilopascals. So the bars will cancel out. So I divide that by 100 and I get 0.0277. And now I have a unit of kilojoules per kilogram kilopascal. Okay? Kilojoule per kilopascal, kilojoule per kilogram kilopascal. Okay? Let me get over here and work on the rest of it. Get over here and work on the rest of it. Let's see here. All the way over here. Okay. Well, let's get out of the kilopascal and get into pascals. So 0.0277, and then I've got kilojoule per kilogram, and then I got a kilopascal. Let me get out of kilopascals and go into pascals. Let's see here. There is 1 kilopascal per 1,000 pascals. Kilopascals cancel out and I get pascals, so I got to divide it by 1,000 again. By the way, I think I'm going to convert out of the kilojoules too. Let's do that. Let's see here. There's 1 kilojoule per 1,000 joules. And actually, if I do that, the thousands cancel out in the conversion here. And so I end up with 0.0277. And the unit I have left over is a joule. So the kilojoules are gone. And I have a joule per kilogram. And then I have a pascal. Now, a joule is a Newton over a meter. Newton times a meter. A pascal is a Newton per meter squared. All right? The newtons cancel out. The meter squared goes at the top, and I have cubic meters per kilogram. 0.0277 cubic meters per kilogram. In other words, specific volume using the compressibility factor. So I'll say compressibility factor is equal to 0.0277 cubic meters per kilogram. Okay? Now let's compare what we got using the tables. Using superheated vapor tables, we got 0.0278 cubic meters per kilogram. That is the specific volume at that temperature and pressure. Using the compressibility factor Z, which we found to be equal to 0.91 using the chart, we get something very similar, 0.0277. Very close. And I was just eyeballing the chart. I was just eyeballing the chart. Okay? So the compressibility factor approach actually did pretty good. Good agreement with superheated vapor tables. Superheated vapor tables. Good agreement. So if you want to calculate some quantities for a gas, you can either use superheated vapor tables or you can use the compressibility factor and the compressibility chart. Okay? Now I'm going to take a pause for a second. We're going to finish up part Z, which is assuming the ideal gas law and cranking away. But I'm going to take a break for a second. Okay, let's finish off the problem by calculating the specific volume, assuming Z is equal to 1, i.e. by the ideal gas law. Okay? So let's finish off the problem by calculating specific volume, assuming the ideal gas law. All right, let's do that. Let's see here. So this is part C, and this is specific volume according to the ideal gas behavior, IGB. So that's when Z is equal to 1. And so we have specific volume is equal to what? The gas constant R times temperature divided by P. Okay, that's when Z is equal to 1. Ideal gas law is assumed to be valid. Let's see here. Gas constant R. Gas constant, where do we put it here? Oh, 0.416. 461, and that has units of kilojoule per kilogram degree Kelvin. And then my temperature is what? 793 degrees Kelvin. 793 degrees Kelvin. And then we got pressure, which was what? 120 bar. 120 bar. Okay, so I crank through that. Let's see here. So I crank through that, go through and do all the conversions. I won't do it here. I get 0.0305 cubic meters per kilogram. So specific volume using ideal gas law or ideal gas behavior is 0.0305 cubic meters per kilogram. Okay? Okay, so we have 3 different specific volumes that we calculated in this problem. Part A was using the steam tables, superheated vapor tables. That is our specific volume. It's 0.27 cubic meters per kilogram. That is the correct specific volume. True or actual specific volume. And then we use the compressibility factor. We use the compressibility factor found of Z of approximately 0.91. And we calculated specific volume of 0.027 cubic meters per kilogram. Very close to the value out of the steam table or the superheated vapor tables. Okay? Very good agreement between use of the compressibility factor Z to calculate specific volume and the actual value from the superheated vapor tables. And then we use the ideal gas law, and we found that we get 0.0305. 0305, okay? And we can see this is not very accurate. We're off by about 10% compared to the true value and compared to using the compressibility factor. Why is that? Because earlier we noted that the reduced temperatures and pressures we're not in the correct range to assume Z is approximately equal to 1, ideal gas behavior. So let me remind you, before, let's see, we had, as I recall, so note, reduced pressure was what, 0.55 as I recall, and reduced temperature. What was reduced temperature? I forgot what that was. It's like 1.5 or something like that, or 1.2. I think it was 1.2 reduced temperature. Let's see here. I guess I'll have to look that up again. Let me check. What was reduced temperature? Let's see here. 700. Yeah, it was like 1.2, as I recall. So reduced temperature was about 1.2, as I recall. 2.5 or something like that. So reduced pressure 0.5, reduced temperature 1.2. Pressure reduced is not less than 0.2. And T reduced is not greater than 2. So we can immediately say that ideal gas law, Z is approximately equal to 1, ideal gas behavior, ideal gas behavior, IGB, ideal gas behavior, IGB, not valid. Okay? We're going to get too much error if we use the ideal gas law to calculate specific volume for this problem. And we saw that. Our error was about 10%. Usually engineers like error be around 2 or 3%, let's say, okay? Okay, this is a lot of stuff here. A lot of stuff we've gone over in chapter 2, properties of pure substances in the notes. Let me show you a table here that you might find extremely useful to keep your head straight on what the various property relationships are, how to get the various properties for the various materials and the phases. If you look at the very back of the notes in section 2.26, you'll see a review of property relationships. So how does this chart work? You start with the top, and you ask yourself whether the material is some kind of a vapor. B here in this expression can be any quantity like specific volume, internal energy, and enthalpy. If B, specific volume, enthalpy, internal energy is greater than B for the saturated vapor, then it is a superheated vapor. So you go over here in the flow chart. If your specific volume is greater than the saturation, specific volume for the saturated vapor, then you can ask yourself, well, it's a superheated vapor. Can I use the ideal gas law? Is IGB valid, ideal gas behavior valid? If no, and you can do that by checking the reduced temperature and pressure. If no, then you use superheated vapor tables. If yes, then you can use the ideal gas law. Then you can use the ideal gas law. Okay? If you are not a superheated vapor, then you could be a saturated mix. So is internal energy, specific volume, or specific enthalpy between that of the saturated liquid and the saturated vapor? In other words, are we within the dome? If so, then we're a saturated mixture, and you can calculate properties using quality. Remember, B here is a variable that represents specific volume, internal energy, and enthalpy. If you are not within the saturation dome, then you must be a supercooled liquid. And then we have all the approximations here for internal energy, specific internal energy, specific volume, and specific enthalpy for a supercooled liquid. And we use these in an example as well. I suggest you keep this table handy, and it allows you to make it easier to do problems where you may have various states and phases to deal with, okay? So I do want to point out this flow chart that you have in section 2.26 in the notes. All right, ladies and gentlemen, that's all I have for today. Next week, we'll be moving on to work, heat, and then after that, we'll be moving on to the energy balance.